Alright, in today's question, we're going to verify that for the Bernoulli distribution, the summation of probabilities for any given value x such that the parameter mu is given is equal to 1. We'll also prove that the expectation of x for the Bernoulli distribution is mu, as well as the variance of x is mu into mu minus 1. First definition that we would want to go over is the definition of the Bernoulli distribution itself. Say x belongs to a set and it can have only values null and 1. Then the probability of x equals 1 given that it is a biased coin will be mu. The probability of x equals 0 such that mu is given is equal to 1 minus mu. This is the probability of a coin flip. This is the definition of the Bernoulli distribution. And in layman's terms, what we can imagine is that there is a coin flip. In layman's definition, let's say that there is a coin and any fair coin will have a 0.5 probability of it being heads or tails. So in this case, if we insert these values where 0.5 is equal to mu, then for a fair coin, the probability of x is equal to 1 given 0.5 is going to be half, and probability of x is equal to 0 given 0.5 is going to be 1 minus half is equal to 0.5. So now let's try to sum up the probabilities for x given mu as the parameter when x is equal to 0 and x is equal to 1. So this is essentially going to be, since x can take only two values, which is 0 and 1, we can split the summation into two. The probability of 1 given mu plus the probability that it is 0 given mu. In this case, if we simply insert the values from the above equation, it's going to be mu from here, and from here is going to be 1 minus mu. And if we add all of this and this gets cancelled, hence we get the probability as 1. And now let's try to solve for the expectation. For the general formula to find out the expectation of a probability distribution is the expectation of probability function f is equal to the summation of probabilities of x for function f of x across all x. In this case, our function f is equal to the probability function. Thus, the expectation for p is going to be the probability of p when it's 0 given mu f of 0 plus probability of 1 given mu f of 1. Now this is equal to the probability of 0 such that given mu is 1 minus mu. F of 0, it's simply the value 0. So we can simply put it as 0 plus the probability of 1 given mu is mu, and f of 1 is simply the value 1. So this is equal to mu. Now let's try to solve the expectation of the variance for f. And here the general format is the variance of f is equal to the expectation of f of x square minus the expectation for f of x the whole square of expectation. In this case, we will use some substitution just so we can simplify our lives a bit. Let g of x equal to f of x whole square. Then the expectation of f of x squared, this term that is going to be equal to the expectation of g of x which implies it's going to be the summation across x for all g of x and then the probability of x. This is going to be equal to g of 0 probability of 0 plus g of 1 probability of 1. Now if we resubstitute the value for g of x is equal to f of x squared, we will get f of 0 square probability of 0 plus f of 1 squared probability of 1. This implies f of 0 is going to be 0 into probability of 0. This entire term goes away. We're going to add it. For f of 1, it's simply going to be 1 square, and the probability of 1 is mu. So hence, so the value of the first term here is mu. The value of the second term is simply mu square. This is what we got from the previous value. Alright, so now if we resubstitute the value that we have found for variance of the function, we get variance of f is equal to mu minus mu square is equal to mu 1 minus mu. And this is the variance for the Bernoulli distribution.